Well, good evening, everybody. Welcome to AP Live. Every night we come to you with, for this particular channel, AP Physics C, Electricity and Magnetism. My name is Roger Siegel, and I teach at Pineview School. We're coming to you live tonight from Sarasota, Florida. And my friend and co-teacher is Kristen. Hello, Kristen.
Hi, everybody. I am Kristen Gonzalez Vega in Frisco, Texas, where I teach at Reedy High School.
Excellent. So Kristen and I go back and forth with the lessons every night, and we're here to hopefully get you what you need to be ready for the AP exam on May 11th. So the first thing that I want to do is I want to start sharing my screen with you, which that doesn't do that, sorry. Here we go. All right, share. All right, good. I'm going to share my screen with you. And I'm going to come over here and let me get started with where we are tonight, okay? And so that here looks like this. All right. And so here we go, sorry. Tonight is day 5, review day 5. We started on Monday, and tonight we're reviewing section 1.5 from the course and exam description. And it's electrostatics, field of other charge distributions. And we're going to look at the electric field from a line charge and in different shapes. This tonight could be one of the most specific and directed lessons that we do the whole season, because it's just about this one particular concept and how it works. Before I get started with that, I wanted to go back and finish a problem from last night. And last night we were talking about Gauss's law and how we can figure out the charge in different places using Gauss's law. And so I wanted to come and take you back to this page so that we could get you some more, just this one last bit done. Okay, so up here we have a solid cylinder of radius A is concentric with cylindrical shell of inner radius B and outer radius C. Both materials are conductors, so that is very important. That is extremely important. We'll come back to that in a minute. The inner conductor has a net charge of Q, and the outer conductor has a net charge of Q, capital Q. Both conductors have a length L, ignore edge effects. All right, good. Now, they want to know, determine the electric field at a distance R from the axis. So here is our distance R, okay? And R is going to go from here to somewhere. Now, notice we first have, A is my inside cylinder, and then to B is the inside surface of my outer cylinder, and C is the outside surface of my outer cylinder. And we're going to go to some R between those. And so what R is that going to be? Well, first we're going to say R is less than A. So that means that we're looking right in here at the charge. Now, I'm going to go back to here because I said this was important, conductors. And this is why this is important. If I have a conductor, all of the excess charge of that conductor lives on the surface. All of the excess charge. So what does that mean? Well, we were told here that the charge on the conductor is Q, is inside conductor is small q, all right? So I've got this small q charge. Now, where is that charge? Well, it's all on the outside. And so since it's Q and it's Q plus, I have all of these plus charges on the outside. Now, when I say that, I want to be very clear. There are still electrons here on the inside, okay? There's still protons and neutrons and electrons in there. What we have on the outer shell is the excess charge, anything that is above, once there's an extra electron for every proton, it will go to the outside. Or if there's not enough electrons, then we have an extra proton on the outside because it's unshielded. So That's what we have. So all my charge is on the middle. So I'm going to use Gauss's law to go ahead and figure out what is my electric field. And so remember, Gauss's law says the closed surface integral of E dot dA is equal to Q enclosed over epsilon naught. Now, this is the interesting part. This is the excess charge enclosed. How much excess charge is enclosed if I am within A? 0. Because all of the excess charge lives on the outside. And so that means that my E field here is indeed 0. Right? Now, if I am between A and B, if I am here, for example, my radius is here, what is the electric field in here? Well, for this one, remember, the way we do this is we create a Gaussian cylinder around my inner charge here. And so that Gaussian cylinder has, if I look at the net diagram of my Gaussian cylinder, and you might want to go back and look at last night's work for this, when I enclose a cylinder with a Gaussian cylinder, I get 0 flux at the end, and my flux here, this is the length of the cylinder, and this is 2 pi r, the circumference of my cylinder. And so what I have then is, let me come down here, get some space. I have that closed surface integral of E dot dA is equal to, and that's my charge enclosed over epsilon naught. Both of these are constant. The E comes out. My surface area of my cylinder that has a flux through it is L times 2 pi r, the length of the cylinder, times the radius 2 pi r, and that's equal to the charge enclosed. Well, that also is the length times, or well, I'm sorry, let's see, we'll make this just as big as it needs to be, because in this problem we're ignoring edge effects. And so we just have, well, we do have our length here, and this is going to be length times Q over the length, be our total Q, and that's E naught. The L's will cancel. And so we're going to get E is equal to Q over 2 pi r L, and that's the length of our cylinder. Now, the reason, one of the reasons I wanted to come back and do this one, let me go ahead and finish. Now, if I'm in here between B and C, that means that this charge here, remember, is Q plus, and that's on here. Now, one of the laws of the way charges behave is that the electric field inside a conductor has to be 0, must be 0. And so how do we make the charge inside a conductor 0 if I've got this charge, the electric field inside a conductor 0 if I've got this charge? Well, the way I do that is this Q is going to pull a Q minus out of this metal, out of this surface. And so this outer shell is going to donate a Q minus to the inner shell. Now, where did it get that Q minus? Because what did it have to begin with? It had capital Q. And so now what we have is the rest of I am failing on this one. So I am going to go back to my notes and punt, but I will come back to this and we will keep moving. Now, what did I want to tell you about this a minute ago? The reason I wanted to look at this problem is because notice what they're saying. They're saying ignore edge effects. All right. Now, this is important because in order to use Gauss's law, we have to have a perfectly symmetric setup. All right. And if we don't have that symmetric setup, we can't use Gauss's law. So tonight's lesson is really about these times when we can't use Gauss's law. So what we're going to do tonight is we're going to look at the fields of other charge distributions, ring, line, and arc. All right. So after today, and I did say a minute ago, this is going to be perhaps the most directed lesson we do. It's very specific and very proscribed. We know exactly what we're doing. And it says derive expressions for the electric field of specified charge distributions using integration and the principle of superposition. Examples of such charge distributions include a uniformly charged wire, a thin ring of charge along the axis of the ring, and a semicircular part of this semicircular arc. Now, we're going to talk about the limits of Gauss's law. Gauss's law is true. There's not a time when it's not true. However, we can really only do this integration easily. It only becomes doable when we have a perfectly symmetric charge distribution. Now, yesterday we talked about there were 3 perfectly symmetric charge distributions. One was a point charge, okay? And a point charge, we put a sphere around that. And so we have an imaginary Gaussian sphere, okay? Our second charge we looked at was a line charge, either a dimensionless line, or we could have a cylinder. And as long as it was long, as long as our cylinder was really, really long compared to how far away from it we were, then we would have, that would be a cylinder or a line charge, okay? And as long, again, as this distance were small compared to this distance, a very long cylinder, then we would use a cylindrical Gaussian surface. And then also, and you'll see this if you look back at last night's work, we talked about if we had a really, really big sheet of charge, we would also use a cylindrical surface, Gaussian surface. By the way, that can be done with a rectangle as well, but we're not going to have to do that tonight. So Gauss's law is true, but we only apply it in the most rarefied air form. We don't use it in very other instances. And if we do have another instance where we don't have symmetry, it forces us to do some integration. So some charge distributions require that we integrate. And so what we do is we just basically integrate all over. We use the point charge equation, but instead of Q, we use dQ, a tiny little differential Q. So I'm going to do one of these, and Kristen's going to do one. And you're going to see that this is something that is going to really make you feel good about all the calculus that you've studied in your life. All right, so this says a thin line of charge Q is uniformly distributed along a length L on the x-axis, A units to the right of the origin. What does the electric field at the origin do to this charge? Okay, so let's take a minute and just make sure we see what we've got. We've got this this line of charge. It is uniformly distributed. It's the same everywhere, this Q. And it starts here at a distance A to the right of the axis, and it ends a distance L from that. It's L long, okay? Now, let's go ahead and take a look at this problem and see how we would do it. And again, you're going to feel very good about the calculus you've done. Now, the way we do this problem is first, we're going to figure out a way to instead of, well, let's talk about first dq, what we're going to do. Now, since this charge is spread out in space, we can't use the point charge and say this vector plus this vector. We have to do an integral and add up an infinite number of these vectors. So I usually just start with E is equal to the sum of a whole lot of tiny DEs. So look, here's a DQ here, and it makes a little field here. That's a DE. That's from that little bit of DQ. And then maybe this DQ over here, okay, it's a really small part. It's further away, so it makes an even smaller DE. And if I can find all the DQs and add them up and add up all these DEs, then I'll get the total total electric field. So that's what I'm going to try and do. And so first thing is, after we get here, we want to say, well, what's dE? Well, dE is equal to K dQ over R squared. Just that. So we have to take, again, every little dq. And so what we need is to figure out how far that dq is from the origin. And the distance that it is, we're going to call x. And remember, this is a little dq. Now, how do I know how much dq is? Well, what I'm going to have to do is I'm going to have to take my total charge here, q, and I'm going to have to divide it by the length. And that's going to give me what's called, I'm going to use the symbol lambda, and that's called the line or linear charge density. Okay, and that is coulombs per meter. Okay, so that's my linear charge density. Now, yesterday we looked at a lot of different charge densities. Just to remind you, I'll put a little star over here. I want to bring that up here. We looked at lambda, which was our linear charge density or our line charge. The small Greek letter sigma is our area density. And the Greek letter rho is our volume density function. Now, this one is a line charge, a linear density function. And so that's how much my linear density is across here. And you're going to see why I need this in just a second. Now, one more thing we're going to do before we're going to take this all home. The distance from here to here, this tiny little dq, is made up of a little bit of length called dx. That is my differential. Okay. Now, here's where the magic happens. dq is equal to lambda dx. Now, let me just stop for a minute and kind of impress upon you how important it is to understand that point before we move on. If I can know now what the q is in terms of x, now I can integrate all along x. And so each little bit is just the length times the density, each little charge. And so I'm going to bring this guy down, and I'm going to say that dE is equal to K, and I'm going to say that my dQ is lambda dx. And my distance, R, is actually this distance x, so that's x squared. And so you can see that the lambda comes out, and so let's go ahead and integrate this. And so that means that E is equal to the integral of all the dE's going, and so this is the integral of K lambda dx over x squared. And the question now, what are my limits of integration? And AP always asks that. And so my smallest value of x, you can see, is here at a. So x is going from a to this distance over here, which is a plus L. And so I'll go ahead and go from a to a plus L. And it's just going to take us a second to finish this. You can see, hopefully here, that the lambda and the k come out front. And so I'm going to finish this over here. This is K lambda, integral of dx over x squared from a to a plus L. And okay. And this, when we integrate this, we're going to get negative 1 over x, K lambda. Let's put the K lambda over here. Negative 1 over x going from a to a plus L. Now, this negative, right away, I know what the direction of my electric field is. I'm going to ignore this negative. I apologize if that's not everybody's happy about that, but let's keep going. All right, so that's going to be what we have is K lambda times the quantity, and this is going to be 1 over A plus L minus 1 over A. And so that's going to be K lambda. And we're going to get a common denominator, A over A times A plus L minus A plus L over A times A plus L. And so what we end up with is K lambda times, in the numerator, we have A minus L. I'm going to again ignore the minus sign, over A times A plus L. Now, last thing before we send it over to Frisco, Texas. Sometimes, a lot of the times, but not all the time, you can look at an answer and ask yourself, does it make sense? And so let's take a look at this answer and say, does it make sense given what we know? Does the electric field, should the electric field equal to K lambda times L over A times A plus L? Now, first of all, we would imagine that if lambda, and I need to do something here. Goodness me, beat me with a wet noodle. That's K lambda. And remember, lambda is Q over L. So that's going to be Q over L times L over A times A plus L. And so again, this is now Q. All right, so the question that I have for you is, does this make sense? How would we increase the electric field? So if I increase Q, would that increase the electric field? Absolutely. What if A increased? All right, now notice there's two A's in here. I have an A squared plus A times L, right? So if I increase A, not only does this part get further away, but this does too. So I decrease my E field by more than 1 over the increase squared. Also, look at the L. If L goes up and A doesn't, I get a bigger rod here, which is, now this part is further away than this. And so it would contribute less if I had the same charge. So it's always good, not always, it's often a good exercise to look at a problem and say, look at an answer and say, does that answer make sense the way a problem is playing itself out? All right. So we've got a few more to do for tonight. Hang tight. Kristen, are you ready for them?
Yes, sir.
Okay, take it away.
Okay, so we're going to look at a ring of charge and what happens to find the electric field. And I'm going to show you a shortcut eventually, but the first thing I'm going to do is kind of show you the long way to show all the steps. So then you can see when I say what the shortcut is, you can understand that it does work out the same way. So I've got a thin line of charge, Q, where the charge is uniformly distributed along the ring. And we want to know what the electric field is at a point on the axis of the ring, X away from the ring. Okay, so the first thing I want you to do is I want you to take a couple of points on the ring and break it up for me. So we're going to make a couple of different little DQs. So let me tell you where I want you. Let's look at this little section right here on top of the ring. And let's look at this tiny little section on the bottom of the ring. So if the whole charge is Q, then I know that my tiny little sliver up here has a charge of dQ. And the tiny little charge on the bottom here also has a charge, dQ. So what I want you to do is at this point right here, I want you to draw me two different field vectors. What would the electric field be at this point due to the top little dQ? And what would the electric field vector look like due to the bottom dQ? So draw me two vectors. Which way would they be? Which way would the electric field be due to the top charge and due to the bottom charge? Okay, so we want to know what charge this is. What's the magnitude of the charge, right? If this is positive Q, then we could say that the electric field due to the top is pointing, well, it's kind of already there for you, isn't it? Down and to the left. So we're just going to call this E from the top, ET. And if I look at the bottom one, it's going to have an electric field up to the right. We'll call that EB for the electric field from the bottom part of the ring. Well, if this is a DQ, right, this is a tiny little differential of the whole charge, then really I don't want to call this E. It's not the whole electric field. It's the DE due to those charges. Okay, so let's look at how we could find just one of these. Let's take this top one right here. How could I find what that one DE is? Well, we just learned a minute ago that we know that DE is K times DQ over R squared. But we've got an angle here, right? We don't like angles. I want to look at the components here, and let's look at which of the components are going to be significant. Are they both or just one of them? So I'm going to break this up into its X component and its Y component. And I'm going to break the bottom one up into its X component and its Y component. What do you notice? I know you see it. If I look at the Y components, I've got a positive Y and a negative Y. And if I'm taking the exact same little DQ here, then those would be the same component. So our Y component is going to cancel out. And we could do that all the way around the ring. The only thing we are going to have left with is our X component. So I'm going to redraw this here. So that we can see our geometry and trigonometry here and what we're going to look at. So here we know this is theta. Doesn't like it on the side of the screen here. So this is R, and this is theta, and this is X. And so if this is also going to be theta, then we want to multiply by what? What do we want to multiply by to get just that X component? We want to multiply by the cosine of theta. Okay, so that'll give us that first one here. Okay, so if we want to then solve for what that is all the way around, well, we got to address what is the DQ, what is the R, right? So you always want to be looking at when you have these different charge distributions, what variables are changing and what variables are constant in your equation, right? Because that's what you're looking to see. How are you going to integrate? For the different charge distributions, there are different things that are changing. And the one before, we had that changing X across. Well, in our ring of charge here, well, we know that this R is staying constant as we integrate around our ring. Okay, so if we also know that that angle theta is going to be staying constant. If our X is constant and we know our R is constant, we know our theta is going to be constant. Okay, but we don't know what theta is, so we need to plug in for theta. What can we plug in for that cosine of theta? Well, cosine of theta is going to be adjacent over hypotenuse, or our X over our R. And what would our R be in terms of our X and our big R that we know, the radius of the ring? So those are things we want to be plugging in. So we're going to say this is DE equals K DQ over, we know that R is going to be equal to the square root of X squared plus R squared. And so we know R squared is just going to be X squared plus R squared. Okay, and then we can plug in that cosine. We're using this, our cosine is going to be equal to X over R, or X over the square root of X squared plus R squared. And this probably is going to start to sound familiar from last night because we did a 2-point charge where we were using these same kind of ratios. And so if I combine these in, then I get DE equals K DQ times X over, this becomes X squared plus R squared to the 3 halves. Okay, so we're all set up now. If I want to find what the net electric field is going to be there, now we're going to integrate. So if I'm integrating both sides and we're integrating it all around that circle, well, the X is constant, the R is constant. The only thing that's changing is that DQ. And if we integrate all the way around, what do we get when we sum up all the DQs? We get just Q. So E is going to equal K times Q times X over X squared plus R squared to the 3 halves. So here's my question. If we had just taken this as 2-point charges, let me get a different color here. Let me use this one instead, actually. Let's use a fresh one. if I were to take this as just 2 point charges instead of my ring, and if each point charge had a Q of our total charge over 2, half the charge was on the top and half the charge was on the bottom, well, we would get the same thing, because remember, we got this equation last night, but since each of them really had Q over 2, but there was 2 of them, well, we end up getting that same thing. So that's kind of a shortcut on the ring, is you can treat the ring like it's 2 point charges. And where each of those point charges is equal to half, let's use little q, right? Each of those is equal to the total charge over 2. So just a little shortcut there. Okay, and then we've got one more question here with a ring, but this time we have half of the ring has 1 charge. It's isolated and it has an insulator between, so that we can have the top half be negative charge and the bottom half is positively charged. And we want to know what is the direction of the net electrostatic force on an electron located in the center of the circle. So if I placed a little electron in the very center of the circle here, which way would that electrostatic force be on the electron? So I know that you can like reason through this, but what I want you to do is I want you to write me a sentence, right? We need to practice our writing. Write me a sentence, not using that the negative charge wants to be attracted to the positive or repelled by the negative. I want you to write me a sentence where you are using that electric field to explain which way the force is. So A, determine which way the electric field is, and then B, tell me how you know then which way the electrostatic force would be on that electron. I'll pause just for 1 second here, have a drink of water while you're doing that. Okay, so let's first look at which way the net electric field is going to be in the center. So if I'm looking at the top half of the ring here, we know that we have a negative charge and we know the electric field is going to be pointing away from positive and toward negative. So if I'm breaking it up, let's just look at kind of 3 different spots here to look at that field. So we've got negative charge here. So we've got an electric field pointing towards the right, upwards. We've got an electric field straight up, an electric field up to the left. Again, what do you notice now about the x components? Well, now the x components are going to cancel, and we're left with a net upward electric force due to the top half of the ring. Let's do the same thing with the bottom half of the ring. The bottom half of the ring is positively charged. Let's again take just a few little segments here. And if this is positively charged, then our dq here is going to give us a de this way. If we look at this one, this way, and the very bottom, straight up. Again, what do you notice? X components are going to cancel. We're left with a net electric field pointing upwards. So we're going to combine for one big net electric field upwards. So what does that have to do with the force on the electron? Well, we know that the force is related to Q times E, but positive charges, remember we said experience forces in the same direction as the electric field, and negative charges experience forces in the opposite direction. So if the net electric field is pointed upwards, which way would the electrostatic force be? It would be downwards. Okay, so making sure that you can explain this lots of different ways using physics, not just repelling or attracting, like kind of going a little bit deeper than that if you can. Okay, so that's all I've got, Roger. If you want to finish us off here.
I guess I want to. Okay. Well, great. All right. Thanks, Kristen. Well, let's go back to some more problems here, and let's do a couple more before we call it a week. You guys are doing great. So here we have, this is a wonderful little problem. It says a rod of uniform linear charge density, lambda, there it is again, is equal to 1.5 times 10 to the minus 5 coulombs per meter, is bent into an arc of radius 0.1 meter. The arc is placed with its center at the origin of the axis shown. Determine the total charge on the rod. Well, the total charge, Q, is going to be the charge density times the length Actually, I'm going to call it S, because usually for we do an arc length, we call that S. And so that's our arc length from there to there. And so that's going to be lambda. And the arc length, since I've got 60 degrees and 60 degrees, that's 120. That's a third of a circle. That's going to be 1/3 times the circumference, 2 pi r. So we're going to do lambda times 1/3, 2 pi r. And when you plug all the numbers in here, what you get is 3.14 times 10 to the minus 6, and that's going to be coulombs. And by the way, that is 1 micropi, if you want. I've never seen an answer come out like that, but that's a micropi. It's 10 to the minus 6 pies. Okay, so then the next piece says determine the magnitude and direction of the electric field. Now here is where we get into, again, the geometric integration. And so we're going to go ahead and integrate this thing geometrically. And so let's put a circle in here. Let's put a an XY and make it easier for me to do this. And let's see what we get from this. Now, what we're going to say is, again, we're going from here to here. And just as Kristen showed us before, I'll bet I can convince you that when I add all these up, the only component I'm going to have is going to be in the X direction, because all the components in the Y direction are going to cancel. And so I only really care about X. And I know that DE in the X direction is equal, again, to DE cosine of the angle theta. Okay, so that's the X direction, and that's the angle, that's theta. And so once again, this one's a little bit tougher, though, than the one before, and I'll show you why in a minute. So we're going to say this is going to be dE cosine theta. And what is our dE? Well, that is k dq over r squared cosine theta. And now, again, that's dE in the x direction. Now, before we changed the theta to a number, to a variable x and y, but I want you to notice what's different here. The r here, the radius, the distance to my dq is always the same. So that's going to be a constant. I can pull that out. But what is my dq? That's what's a little tricky geometrically, but I'll bet some of you remember how to do this. So I've got a tiny little angle here, and that's my d theta. Okay, and dq is going to be this little ds times lambda. That's lambda times the little bit of the arc. But what is that little arc length? Well, that's going to be r d theta. So what we're doing is we're going from the geometry formula that the arc length is equal to r theta. So ds is going to be r d theta. So what we then have is we have k, and then dq is going to be lambda r d theta over r squared cosine theta. And I'm going to integrate that from, now I could go from -60 to 60. That would be my cosine. But because of symmetry, I'm going to make it even easier. I'm going to go from 0 to 60. All right. And so if you look here, one of the r's cancels. Everything else is a constant except for the cosine and the theta. So what I get then is I get 2k lambda over r times the integral of cosine theta d theta from 0 to 60. All right. And so that becomes quickly, that's 2k lambda over r sine of theta from 0 to 60, and 2k lambda over r. The sine of theta is the square root of 3 over 2. Now, k is 9e to the 9th. That is our Coulomb's law constant. Lambda is 1.5 e to the -5 coulombs. We have our radius, which is 0.1 times the square root of 3 over 2. And so when I'm all done, I get 2.3 times 10 to the 6 newtons per coulomb. All right, that's a fun one. I want to do one more for tonight, and I want to move on to skip this one here, and I'm going to skip it. And by the way, yeah, and let's go down to this one. All right, so because this is one of the things we talked about tonight, why can't I use Gauss's law? So notice here we've got this lambda, and notice my setup. Here's my y is equal to c. Here's my point. Here's my charge right here. So I've got this charged rod, and again, it's got this this linear charge density of lambda, and that's going to be lambda coulombs per meter. All right, is there a single Gaussian surface that can be used with Gauss's law to derive an expression for the electric field? Now, I think I already gave it away, because at the beginning of the hour, that's what I talked about. So the answer is no, you can't use Gauss's law. Now, I want you to just try and think in a sentence or two, why can't we use Gauss's law? I hope that one of the words that you're going to use to say why we can't use Gauss's law is the word symmetry. And the fact is that there is not symmetry in this problem. And since it's not symmetric, we can't use Gauss's law. So Gauss's law requires a high degree of symmetry of the electric field. To use Gauss's law, C would have to be much greater. I'm sorry. C would have to be much less than A plus B. Now, when we did this last night, we talked about an infinite line of charge. Then we used Gauss's law. Or we did a problem at the beginning of the hour, and it said to ignore the edge effects. And again, that's code for it's okay to use Gauss's law. When they tell you to ignore the edge effects, it means you can kind of fudge on the lack of symmetry. They're saying, don't worry about the lack of symmetry. Go ahead and use Gauss's law. But in this problem, the lack of symmetry is a signal for us to not use Gauss's law. Now, the last thing before we go is I want to look at this one. And, you know, we have no idea what this year's test is going to be like, but this is a problem that I think really a lot of students struggled with it when it came through because they weren't used to doing the integration. And it says one of the two expressions is not correct for the horizontal and the vertical component of the electric field. Which one? And so this is going to be our last problem for the night. Let's take a look. Which one of these do you think is wrong? Now, I think from the work that we did last night and the work that Kristen just did, we keep seeing this this distance to the 3/2. That is a consistent a reoccurring part of our solution. It's this one that's wrong. Okay, so which one is not correct? The vertical. Now look at how these guys at AP, I tell you, they always make it so hard. 2 mistakes, and you're like, wait a minute, 2? I thought it was just because it was this one. But take a good look. Take a really hard look. When you integrate, which way do you integrate? When you are solving for, the horizontal, here's our DE, here's our horizontal component, here's our vertical component, okay? Now, when you're solving for that, you're always doing what? Well, you're marching across from B to A. And since you're going from B to A, ladies and gentlemen, or I'm sorry, from negative B to A, you're going dx, not dy. Look at that. So if that kind of problem came up, don't forget to look at the differential because it could show up. All right, next week, we are going to keep working on our unit of our review of electrostatics. We are going next week to start looking at potential. I think on Tuesday. So potential is a really big challenge for a lot of students, but we're going to get you through it. I think it's called height, but we'll come back to that. We hope that you have a great weekend. Kristen, how's it going in Frisco?
It's great. It's Friday night, almost time for some dinner, and hope you guys have a wonderful weekend.
Excellent. So again, thanks for joining in. We hope you're having fun. We hope you're finding this helpful. And if you need any more resources, see the AP website because they've got so much to help you study for this exam. Can't wait to see you on Monday. Thanks a lot. Bye-bye.